Have you ever just looked up at the night sky and wondered why the universe is the way it is? I mean, why does it all seem so perfect, so balanced? Well, today we are going to tackle one of the biggest, most mind-bending ideas in all of cosmology that tries to answer that. It's called the theory of cosmic inflation. Let's get into it. So let's start with a puzzle, a real cosmic mystery that kept scientists up at night for decades. When we look out at the universe, on the grandest of scales, we see this incredible, almost impossible level of perfection. And this one observation really challenges what we thought we knew about the Big Bang. You know, the Big Bang theory is amazing, right? It's one of the greatest achievements of science, but it's not perfect. As great as it is, it left us with these two huge, glaring puzzles. And we're not talking about minor details here. We're talking about fundamental questions about the very fabric of reality. Okay, first up is something called the horizon problem. And this one is a real head-scratcher. It gets right to the heart of why our universe is so astonishingly uniform, no matter which direction we look. So, imagine we could look at a baby picture of the entire universe. Well, we can. It's called the cosmic microwave background. And here's the bizarre part. When we measure the temperature on one side of that picture, it's pretty much exactly the same as the temperature on the complete opposite side. We're talking 2.725 Kelvin, almost everywhere. So, how? How did these two completely separate regions of space coordinate their temperatures so perfectly? Because according to the standard Big Bang model, they are so far apart that they shouldn't even know the other one exists. It's like they've never, ever been in contact. And you have to remember, the absolute fastest anything can travel is the speed of light. And since the beginning of time, there just hasn't been enough of it for a little pocket of light or heat or any information to travel from one side of the observable universe to the other to say, hey, let's all be 2.725 Kelvin. It's a huge problem. Think about it like this. You pour cold milk into hot tea. At first, you've got hot parts and cold parts, right? You have to wait, you have to stir it for everything to mix and reach the same temperature. But the universe? It's as if it mixed itself perfectly and instantly across these unimaginable distances. It just doesn't make sense. So the uniform temperature is one mystery, but that's not the only one. The second puzzle, known as the flatness problem, is just as baffling. And this one is all about the actual shape of space-time itself and what that means for the ultimate destiny of our cosmos. See, the fate of our entire universe seems to hang on this one little number, its overall density. How much stuff is in it? If there's too much stuff, gravity eventually wins, and everything collapses back on itself in what we call a big crunch. If there's too little stuff, the universe just expands forever and flies apart. But here's the thing. All of our observations show that our universe is neither. It seems to be perfectly balanced, walking a razor's edge right between those two fates. We call this a flat universe, where the density is at this exact, precise, critical value. And the odds of that happening by chance are, well, they're astronomical. I love this analogy. For our universe to be so incredibly flat today, after 13.8 billion years of expansion, it means that its density in the very first fraction of a second had to be fine-tuned to an unbelievable degree. It's like we hit a cosmic bullseye from billions of light years away. It's just too perfect. So you have these two massive problems, right? The uniform temperature and the perfect flatness. Then, in the early 1980s, a physicist named Alan Guth came up with a radical idea. A single concept that could solve both of these cosmic puzzles in one go. He called it cosmic inflation. Guth's idea was this. In the very, very first moments after the Big Bang, I'm talking a tiny fraction of a second, the universe went through a period of unbelievably rapid, exponential expansion, a growth spurt of truly epic proportions. And when I say a tiny fraction of a second, it's hard to even wrap your head around how short a time this was. The whole thing was over and done with in about 10 to the minus 32 seconds. It's a blink of an eye, but not even. It's a trillionth of a trillionth of a trillionth of a second. Just wow. And just to give you an idea of the sheer scale of this growth, in that tiny instant, the universe expanded by a factor of at least 10 to the power of 28. That's the same amount of expansion that happened over the next 13.8 billion years. It's almost unimaginable. So what could possibly cause something like that? Well, the theory goes that it was driven by this bizarre, exotic state of matter called a false vacuum. And get this, it created a kind of repulsive gravity. Yeah, gravity that pushed things apart instead of pulling them together, causing space itself to expand exponentially. So, okay, this is a wild idea. But how does this one flash of incredible growth solve both of our cosmic mysteries? This is where it gets really, really elegant. Let's start with the horizon problem, the temperature thing. Inflation solves it beautifully. The idea is that before this huge expansion, the entire universe that we can see today was once packed into a tiny, tiny connected region, smaller than a proton. In that cozy little space, everything had plenty of time to mix and reach the same temperature. Then, whoosh, inflation stretched that uniform region to the cosmic size we see today. Problem solved. And what about the flatness problem? Well, the solution here is just as cool. I want you to imagine the three-dimensional fabric of space as being like the two-dimensional surface of a balloon. If the balloon is small and wrinkled, you can easily see the curves. But now, imagine you inflate that balloon to an enormous size, like the size of the Earth. From your perspective standing on it, any tiny patch of that surface is going to look perfectly flat, right? The wrinkles and curves had been stretched out. And that's exactly what inflation did to the universe. It stretched the fabric of space so much that any initial curvature was just smoothed out, leaving us with the flat universe we observe today. It's just a brilliant solution. So, there you have it. Inflation solves everything, case closed, right? Well, not so fast. While it's an incredibly powerful idea, it's not quite the end of the story. Inflation is, without a doubt, the cornerstone of modern cosmology. It explains so much so elegantly that most scientists accept it. But it is still a theory. It makes other predictions that we're still working to test. Scientists are pushing the limits of our technology, looking for that definitive proof, that smoking gun that will confirm this incredible idea once and for all. And that really is the beauty of science, isn't it? A great answer like inflation doesn't just end the conversation. It opens up a Pandora's box of brand new, even more profound questions. Things like, if inflation happened once, could it happen again? Could it mean our universe is just one of countless others in a vast multiverse? It's a powerful reminder that the more we learn, the more we realize how much more there is to discover. The quest for answers continues.